So again, motion is that change in position relative to a reference point, and a reference point is the point you pick to make sure that that object's moved by referring to. That's why it's called a reference point, or comparing it to its position relative to something else. So the example they give here, and it does matter which figure comes first. So they've labeled figure one and figure two. So you've got a car, and in this picture, it's static. So you don't really have context for what's happening. There's nothing to suggest motion. So you're going to need a different frame. So you have to have a second frame. You have to have two different pieces of information. And this second piece of information, compared to that tree, it looks like the car's moved to the left. Well, that reference point allows you to say, well, it was on the right, now it's on the left. This happened after the first figure on the left. So it appears that the car is moving to the left, especially with reference to that tree. Now, the important thing about labeling the figures is it gives you a timeline. And that's actually where this time portion plays in, that some time has to pass in order for that object to move. And you're going to have to look at its position at that later time to be able to prove that it moved. And so we're going to need multiple data sets. So that should go ahead and let you know we're going to see multiple time data, and then consequently multiple position data. And we're going to look at that relationship. Well, if you know anything about tables, generally a table suggests what? That we're going to be using what to describe the trends in that table. What do you use to describe trends for tables of data? What tool? This is a question for you all. Right. It is a graph. So anytime you have tables of data, you're going to have trends between two variables, and you want to look at the relationship there. One of your best tools is always going to be a graph. Different graphs work for different data. We're largely going to be using line graphs and looking at generally linear trends throughout most of this class. So if you are not familiar with graphing, if you're not super confident, that's a skill we're going to be working on throughout the semester, and it's definitely something that you're going to grow in because you're just going to have to do it so often. So when we're moving through space, we can prove motion happens by having a reference point and changing our position. Well, let's talk about the specifics of changing our position. Physics is all about being very clear and being able to communicate with absolutely no, uh, really absolutely no ambiguity or vagueness. So we've got two kinds of position change. We can talk about it being a distance change, so the whole stretch of position change being a distance, or we can talk about it being total displacement. So distance is going to be a little bit more vague or excuse me, uh, I'll talk about vagueness with displacement in just a second. I'll kind of hold off on using that example. So distance is how far an object is moved, and we're going to use meters to describe that, but it's really this idea of total steps taken. So if we look at our diagram on the screen, we have a starting point and a finish point, but this red line is going to represent the actual path taken to get there. So the big idea here is there might be an obstacle that makes you not move in a straight path. That's pretty common. Maybe this is a neighborhood, maybe there's a mountain or a lake somewhere in this big white area. You have to go around it. So that's going to be quite a few steps. You're going to go further having to go that way than you would if you went a straight line. And distance accounts for that because it doesn't really care what direction you're moving. It just cares how many steps did you put forward. And at some point, your forward was pointing in a different direction. Now, displacement is going to give you a straight line answer. And what it does is it just cares about the 2 points at the beginning and the end and the path taken to get there. So the distance and direction of an object's change in position from the starting point. So it's distance, but I don't want you to think it's this distance. It's just this idea of the length of distance traveled from the starting point. That's the really important statement there, is that it's comparing it to where you started it. So even though you went all the way around over here and you came all the way back here, I'm going to go ahead and let you know in this class and even in a regular physics class, you're going to need calculus to really accurately describe this path. So what we endeavor to do right now, we're using really, really simple algebra, which is about as far from calculus as we can get. And so we turn it into a straight line. So it's put there, even though it's a slightly less specific answer, because these are all the specifics, you would get lost in the specifics. There's a sea of information just in that line right there because it's not simple. It's complicated. It's changing. Here, we just care about where we started and where we ended. And we do this in physics because you can actually over select data, if that makes sense. You can select way too much data to be able to handle. And if you can't do it, you need like a computer to run this, and you would need a computer to run this. Then you're kind of defeating the purpose of intuitive physics, which is really where we start. So if you want to become a physicist, you might well, study the uh, path here. But right now, and even into college, you're going to make a straight line distance there just to try to simplify it and make the math a little bit easier, to practice the ideas without drowning in the real difficulty that comes in physics. Because if you weren't aware, physics is actually where calculus comes from. Calculus is used to describe changing things, and physics is, well, everything's changing pretty often. So calculus is used very, very heavily in upper levels of physics, which is why we simplify things. So displacement includes the direction. Now that's an important idea. This direction comes out of this simplification. So it's that straight line direction and distance that we're paying attention to in displacement. So it's how far are we from where we started. And it's all about specifics. So if you're wondering why does it care about a direction, I want you to think about an idea. And I'm going to try to switch my share just to quickly share this concept. If I tell you I'm going to move, I don't know, 5 meters, and that is about 15 feet for anybody who's, American units only. We're going to draw in. What I'll do is I'll make this a little easier on myself. So we're going to have a cross here. You're going to see this idea a little bit later, but I just wanted to introduce it now. So you start here. This is your origin. And what we do when we compare to where we're starting is you give yourself almost a grid-like set of information so you can be very, very specific. If I tell you I'm going to move 5 meters from this position, we'll just say that this is about 5. It's a little bit low, but that's all right. So I would draw, excuse the non-circular nature of this. There we go. So I would draw a circle here, and 5 meters could put me anywhere on that circle. So that's going to have a radius of 5, and anywhere on the circle could be where I am if all I told you was 5 meters. That's a distance. It doesn't care about direction. It's just very vague. It's not super specific. However, if I tell you, well, I'm going to move 5 meters to the right, so we can describe this is right, I might end up right there on the line. You'll know exactly where in space I am compared to where I was to begin with. But if we set, let's just say this is a top-down view, we call this north, south, east, and west. This starts to get very useful because let's just say you're a plane and you don't want to run into another plane. Well, you got to know where all the other planes are. So you have to compare to a standard positioning system, and a compass makes a really good standard. So let's say I want to move 5 meters northeast. That gives a specific placement, and I could describe exactly how far northeast if we want to get specific. But it's going to take it from the entire circle to at least this quadrant here, which will be a little bit more specific. So what we're going to do is we're going to focus on the difference between vague answers and specific answers. And those vague versus specific answers are really what physics focuses on. Is you want to be specific when communicating so that it is a very unambiguous job for the reader. The reader needs to be able to do whatever they're doing quickly. That's kind of the point of physics. So we're going to switch that share back. So we're going to come back to this idea, distance and displacement. So this comes together in a weird way in a track. If you think about it, and this is in your notes, if you have a 400-meter track here and you run all the way around it and you come back to the same place, so your distance, which does not care about direction, it has absolutely no reference points, it's just the total number of steps taken, that would be 400 feet, all right, because it's a 400-foot track, or 400 meter, excuse me. Now, do this in a context of displacement, and displacement cares about where you start and where you end, and it's calculated by final position minus initial position. So if you end up in the same place, which running around that oval would put you back in the same place, it's going to cause you to have zero displacement. So you'd have 0 meters of displacement, which I believe is number 5 on your notes. So that concept is a little bit odd, and I've got a video that's going to help hopefully back this up as we kind of move into, and it's going to talk about these two ideas of scalar versus vector. And scalar is a quantity that describes only magnitude, and magnitude means number. It means how much. It's like quantity. That's another way to say that. And a vector is a quantity that describes the magnitude, the quantity, the number, and direction. So I want you to think about this like this is vague. This is just a number. It could be off in any direction. And sometimes you don't need a direction. Like with degrees, you know what 38 degrees Celsius means or what 100 degrees Fahrenheit means. 27 watts here, what you might find on a light bulb, there's no possible direction, right? You don't need to specify that. A vector is more specific. A vector is like an arrow. It's going to be pointing in a direction, and it's going to have some length. So the length would be a number. So 10 meters per second and 8 meters are examples they give here. And the direction, upward or south, makes it more specific. Again, when we're communicating, we want to be very clear, very specific, and a vector is the more clear version of a scalar. The scalar is going to be just a number. It's vague. It doesn't have context. That vector is going to be that same number, but with addition of context, south, upward, something along those lines. So definitely something to consider, that if we want to be specific, we want to use vectors, and displacement is a vector. Scalar would be your distance. It doesn't care about direction. So what we're going to do now is we're going to go watch that video. That video is made by GPB, which is Georgia Public Broadcasting, and it is a state-funded. It's a PBS run, so it's public broadcasting system. And then subset GPB, which is going to be the Georgia version of that. So it's state-funded educational stuff that's aimed at physics. And it's a really good program. We're going to watch several videos. We have 2 for you today, but we're going to watch several videos throughout the semester. And they're all local. So the places they go, the things they talk about, they're in Georgia. At one point, they go to Six Flags Over Georgia. There's a couple other places they visit. The one we'll watch a little bit later is in Atlanta. So it's all local. They just have a good production quality too. And I like supporting Georgia's produced, because like any public programming that's educational is generally good stuff. All right, so without further ado, we'll go ahead and watch this video that describes the difference between distance and displacement, focusing on scalar versus vector.
If you're going on a trip, you might want to know where you are, where you've been, and where you're headed. Thanks to physics, you have some helpful tools to keep track of your position. I'm here in Alexander Park in Snellville, Georgia, and we're going to use this place to talk about a couple of those tools called distance and displacement. Let's start with distance. Distance is a measure of how far something's traveled. The SI unit for distance is meters. Now, if you remember in Unit 1, we talked about the difference between scalar and vector quantities. Scalar quantities only have a magnitude, while vector quantities have both a magnitude and a direction. Distance is a scalar quantity. It's only the magnitude of how far we've traveled. The direction we moved in doesn't matter. So let's say Onzer is standing on a number line. He's starting from 0, which we'll call his origin or his starting point. If he moves 2 meters to the right, the distance he's traveled is 2 meters. Now let's say he moves 4 meters to the left. His total distance from his origin is 2 meters plus 4 meters, which equals a total distance of 6 meters. With distance, the direction you travel doesn't matter. So even though he went 4 meters in the opposite direction, the distance will always be a positive number. Now what if he walks 3 meters to the right? The total distance he's traveled is 9 meters. Again, when measuring distance, the path he takes between an origin and destination matters. So even though he ended up only 1 meter away from his origin, his total distance traveled is still 9 meters. But what if Onzer didn't want to know the path he took throughout his journey and only cared about the difference in meters between his starting point and ending point? That's where displacement comes in. Displacement is an object's overall change in position. Just like distance, the SI unit for displacement is meters. Displacement is a vector quantity, which means it has a magnitude and a direction. So let's go back to our number line. If Onzer moves 2 meters this way, the distance he moves is 2 meters, just like before, but his displacement is 2 meters to the right. Now, if he moves 4 meters in the opposite direction, the total distance he's traveled since starting is 6 meters. However, his displacement is negative 2 meters. So if he moves 3 meters to the right, again, his distance adds up to 9 meters, but his displacement for the whole journey is 1 meter to the right. So why is that? We know our displacement is the difference in meters between our initial position and our final position. That means the route we took to get there doesn't matter. The only thing that matters is how far we are from the origin and in what direction we ended up. So his distance was 9 meters, but his displacement was 1 meter to the right. But enough with number lines. Let me demonstrate using a grid. Where I'm standing right now is my starting point, or my origin. On this grid, north is up, west is to the left, south is down, and east is to the right. Let's call the origin point A on the grid. I'm going to move 4 meters to the right, or eastward, to what we can call point B. Next, I'm going to move 3 meters north to what we can call point C. The total distance I traveled since I left point A is 4 meters plus 3 meters, which is a total of 7 meters to get to point C. With distance, we only need to know the route that we took to go from our origin to our destination. But with displacement, we only need to know the origin and destination and the shortest route between the 2 points. In my case, my displacement is how far point C is from point A if we drew a straight line between them. Knowing that, we can figure out the displacement. This looks like a job for the Pythagorean theorem. The equation, if you remember, is a squared plus b squared equals c squared. A is the distance AB, which is 4 meters. B is the distance BC, which is 3 meters, and C is the distance AC, which is our displacement. If we plug everything in, we see that 4 squared plus 3 squared is equal to c squared. So 16 plus 9 is equal to c squared. Hence, c squared is equal to 25. If we take the square root on both sides, we find out that c is equal to 5 meters. So even though the distance we traveled in our journey from A to C is 7 meters, our displacement is 5 meters. Remember, displacement is a vector quantity, so it has both magnitude and direction. So our displacement is actually 5 meters northeast. To summarize, distance is a scalar quantity. It's the magnitude in meters of the path an object takes from its origin to its destination. Displacement is a vector quantity. It's the difference in meters between an object's origin and destination and the direction it occurred in. These differences will start becoming very important when we start to calculate motions of objects in later segments.
Alrighty, so one of the things you're going to notice there is that there was algebra there immediately in the Pythagorean theorem. So we might, we, I don't think we'll ever have to use the Pythagorean theorem. If you follow through and do any more physics later, or have a physics class in college, you will have to see that in the form of triangles that you're going to have to end up dealing with. So trigonometry and triangles do play a role in physics as well. It's not something we're going to see, but it is something to let you know that the math here is usually the thing that gets people. If people get scared off from physics, it's almost always the math that gets them. So you just got to stay on top of it and practice it. It becomes a little bit easier. All right. So we're going to go ahead and head back in here. Now, we talked about displacement versus distance there. And again, that displacement cares about direction, and it refers to the starting point and the ending point, and is specific in that it mentions the direction taken to get there. And distance is just going to be the total amount of distance traveled, or the total steps taken idea. Distance is scalar, and displacement is vector. Now, you don't see these in your notes because this is honors side note. So just note that this is just a concept that we're going to talk about. You're going to see me mention vectors later, which is why we put it in here. This concept, as she mentioned, is really important for later videos, or what we have later lessons, because we're going to talk about other vectors, and it's really useful to go ahead and get that idea hammered out. So this last side note we're really not going to pay attention to is how you add vectors. It's the same idea that she showed you with the 3 meters in one direction, 4 meters in another, and it was a 3, 4, 5 triangle. You end up using a grid line and some geometry to help you out. So because it's not in the notes, we're going to keep on moving so that we can get through those notes, and particularly through the practice problems we're going to see today. So speed and velocity is the next concept we're going to cover, and speed and velocity is that first relationship we're going to explore that puts time and a change in distance, or what we call displacement, together. All right, so we're going to really put those two ideas together. This is where that space-time continuum starts to show up, that idea that space and time are tied. And we can describe how something moves through both space and time by using speed and velocity. So speed is a measure of how fast an object is moving, and the way we're going to look at some units later, but it's going to relate position and time, and it does not include a direction. So speed, if you think about speed limits on the highway, there's no direction stated, like it's not 65 or 70 miles per hour forward. Well, because think about all of the direction changes that happen on highways and roads. You're not ever going in a straight line direction. So if you change your direction, you would not be going the same speed, or you wouldn't be going in what we're going to find out is the same velocity. So speed doesn't change. It's that idea of total steps taken in the same way that distance is. It's going to be what your speedometer reads out at any given point. Even if you're taking a turn and changing direction, you're still going forward in reference to your car, and your speed doesn't really change. So we'll see that idea in just a little while when we actually look at what makes these up, like their actual formulas. So velocity is the rate at which an object changes its position. Notice how much more specific this sounds. So velocity, rate at which an object changes its position. Very specific there. Rate of how fast an object is moving. Kind of vague. And we're actually going to find out that speed is a scalar quantity. Remember, that's just a number. It doesn't use a direction, and thus it's a little bit more vague. Velocity is a vector quantity, and that's because it uses direction. So it's how long it takes an object to get from point A to point B. It cares about the beginning point, point A, and the end point, point B. So it's going to include a direction and the actual distance, the magnitude there. So velocity is speed with a direction, or you could think about speed as velocity without a direction. All right, so speed is scalar, velocity is vector. The easiest way for me to remember that is the fact that they both start with the same letter as the kind of quantity they are. Speed, scalar, that's S, and then velocity, vector, that's V. That's a pretty easy way to remember that. Velocity is a vector for a specific reason. We actually find out that if you remember, distance is a scalar quantity and displacement is a vector quantity. So because you use distance to calculate speed and displacement to calculate velocity, this is what gives them either their scalar for speed or vector for velocity nature. So speed is distance over time, and this is why it doesn't care about a direction. It just cares about how many steps forward have you taken and how long did it take you to do that. It's the magnitude of velocity, just the number, just the quantity. So the equation we'd use for that would be S is equal to D over T, D standing for distance, T standing for time, and of course speed standing, or S standing for speed. Now velocity here is displacement over time. So that's going to be speed with a direction. So it cares about point A and point B, and V is going to be the letter we use for velocity, and D over T. Now you will see me, and this is going to happen today. I'm going to go ahead and get you used to this. I'm going to be writing D as X because in physics, very commonly, you're going to see equations use X for distance change instead of D. That's because D is also density. There's a couple other things that D is used for, and X is pretty universally used at a higher level. So if you wanted to continue forward, we'd be practicing good skills for that. The SI units for distance and displacement, because they're position changes, are going to be meters. That's the SI unit for meters, or for distance, excuse me. Time is going to be seconds. So we're going to be using seconds almost always. You will see hours and minutes occasionally when we're doing practice problems, but for clear communication, we want it in meters per second. And then speed and velocity, because they are either distance over time or displacement over time. Distance and displacement both have meters as their unit. Time has seconds as its unit. So speed and velocity is going to have the units of meters per second, which is m over s. You could write it like this in a sideways fashion, or you could put it over the kind of have it as a fraction of m over s. Either one works. It means the same thing. So this is just a little pun here. Says velociraptor is equal to distraptor over time raptor. All right. I promise you there are shirts with that on there. So just be glad I'm not wearing the shirt. It's not a bad pun. So it makes us two great things, dinosaurs and physics. Who doesn't love both of those? Lots of people. So scalar versus vector, this idea, it just really wants you to hone in on this concept that speed is a scalar and velocity is a vector, because distance is scalar and distance is used to solve for speed, and displacement is a vector and displacement is used to solve for velocity. So they specify right here, this is something you're going to see in your notes. It's kind of at the bottom of that page to the right. That speed, no matter which direction is pointed, is going to have the same number. It doesn't specify what direction, so you're never going to have any specifics on those numbers. Now, velocity, however, is a vector quantity. So this arrow has a direction, and we, in this case, are considering rightward to be positive and leftward to be negative. So the general rule of thumb, it's not always the case. You technically kind of get to pick, but what most people default to is the same thing that you see when you're graphing on an XY plane, that up is positive, right is positive, left is negative, down is negative. So you would see up as being positive, down as being negative, rightward being positive, leftward being negative. And that's the one that I'm going to default to when we do our work. So just be aware that that's going to be what we see most often. And velocity, by specifying, is plus 2 meters per second. And there's that either means it's going up or rightward or really forward, and this might be going backward. So we're going to get to this idea of two kinds of speed. You're going to see her mention instantaneous speed and average speed in the video we're about to watch, and then we're going to come back and we're actually going to look at this concept and explain it with a little bit more detail. But we're going to go ahead and switch over to that last video we have, which goes through and it wants to detail the difference between speed and velocity. It's going to get into these ideas of scalar versus vector. it's going to mention graphing. So I want you to pay attention to the graphing. Don't get scared off by it because she's going to mention a couple words. I'm going to hopefully smooth that over once we're done watching that video. And we won't get to graphing till next week, but it will give you all the major basic ideas that go along with this, and it's going to do it in a pretty cool context. All right, so like I said, this is located in Atlanta. So going to, yep, we're sharing computer sound.
We've come to the Porsche Experience Center test track to talk about speed and velocity. And if we're going to do so, we might as well make it interesting.
Like I said, we'll see several videos throughout the semester.
In our daily lives, we may use the terms speed and velocity interchangeably, but in physics, speed and velocity are two very different things. In this segment, we're going to find out how and why this difference matters. The cars speeding behind me are moving with a lot of speed, but what does that mean? Speed is the rate at which an object covers distance. The SI unit for speed is meters per second. It's a scalar quantity, meaning it only has a magnitude. For scalar quantities such as speed, the direction the object is moving in doesn't matter. If the car keeps moving just as fast as it was before, except this time it's going the opposite direction, its speed still remains the same. Just because the car is moving in the opposite direction doesn't mean the speed is negative. Speed will always be a positive value. We calculate the average speed of an object by using this equation. The average speed in meters per second is equal to the total distance traveled in meters divided by the total time taken in seconds. Let's work through an example. When a car makes a lap around the track, we can calculate its average speed using the distance it traveled and how much time it took. One lap around this track is 1,600 meters, and the time it takes this car is 55 seconds. So the average speed was 1,600 meters divided by 55 seconds, which is 29.1 meters per second. That's pretty fast. Okay, we've talked about speed as a scalar quantity. What about velocity? Velocity is a vector quantity. It means it not only has a magnitude, but it also has direction. The SI unit for velocity is also meters per second. So when a car speeds past again, its speed is 71 miles per hour, or 30 meters per second. But its velocity is 30 meters per second going right. Average velocity is an object's change in position, or displacement, over change in time. We can calculate it using this equation. An object's average velocity in meters per second is equal to its change in position, or its displacement, in meters divided by the change in time, in seconds. When solving this problem with velocity, it's important to establish a frame of reference. Let's go to the track for an example. Say that right is the positive direction and left is the negative direction. A car is stationary at our origin point, point A, facing right. It's going to speed towards point B and turn around to stop halfway back to point A at point C. Would the average speed and the average velocity of the car over this journey be the same? Well, there's only one way to find out. It took the car 7 seconds to complete its journey. The total distance it traveled was 24 meters. This means that the average speed was 24 meters divided by 7 seconds, which is 3.43 meters per second. However, the total distance traveled by the car is different from the total displacement. The car's displacement only takes into account the point-to-point difference in meters between the origin and the final destination. The displacement from point A to point C is 8 meters. This means that the average velocity over the journey is positive 8 meters divided by 7 seconds, which is positive 1.14 meters per second, or 1.14 meters per second to the right. So it's possible for the average speed and the average velocity to have two separate values, even for the same journey. To recap, speed is a scalar quantity, which means it has magnitude only. Velocity is a vector quantity, meaning it has both magnitude and direction. But how are we supposed to know which direction is positive and which direction is negative? Good news, it's our choice. We pick our own negative and positive directions. So when you're given a problem to solve, indicate which direction you've picked to be positive. Whatever answer you get should reflect that choice. We usually treat right and up as positive and left and down as negative. So when the car was going from point A to point B, it was traveling the positive direction because we've designated right as the positive direction. If the car went from A to B in 4 seconds, then its average velocity was 4 meters per second going in the positive direction. But when the car was going from point B to point C, it was facing the other way. If it did so in 3 seconds, then it had an average velocity of 2.67 meters per second in the negative direction. Now, let's talk about the difference between average velocity and instantaneous velocity. Average velocity, as we've been discussing, is the displacement divided by the change in time. We calculated the average velocity of the car going from point A to point C. But what about the journey itself? The average velocity tells us the overall velocity over the course of the entire journey. The instantaneous velocity is the velocity of an object at a specific point in time. Let's look at the car as it was starting to accelerate and freeze it right there. At the time 0.5 seconds, its instantaneous velocity is 3.27 meters per second to the right. As the car speeds up, its velocity increases. What if we sped up to right here at 1.5 seconds? Its instantaneous velocity is now 9.81 meters per second to the right. Remember, the instantaneous velocity is the velocity of an object at a specific moment in time. Another important term to know is constant velocity, which is what we call unchanging velocity. Okay, so we've learned what velocity is, whether it's average, instantaneous, or constant. But how do we represent it? If we have a position time graph, we can use it to learn about an object's velocity. In a position time graph, the time elapsed will be shown on the x-axis and its position shown on the y-axis. This graph shows a constant velocity, which on a position time graph looks like a straight line. By looking at the slope of the line in a position time graph, we can learn about an object's velocity. It makes sense that this object is moving at a constant velocity because the slope of the line is not changing. We're covering the same amount of distance in the same amount of time. We can calculate the constant velocity by finding the slope of this line. If the velocity wasn't constant, we can calculate the average velocity by drawing a line between 2 points in time and find out the slope of that line. If we want to know the instantaneous velocity, or our velocity at a given point in time, we can draw a tangent line from that point in time and find the slope of the tangent. We can also have graphs that look like this, with the line going up and down. This point indicates I'm moving in the positive direction away from my origin. This would be me moving at a constant velocity away from my origin in the positive direction. This point right here would indicate me turning around and moving at a constant velocity in the negative direction. It doesn't mean that I'm going any slower or faster. The negative slope just means that I'm moving back toward the origin in the negative direction. Remember, the slope of a line on a position time graph tells us the velocity of the object. For a more detailed analysis of position time graphs, see Unit 2, Segment D on graphing motion. We've talked about speed and how to calculate the average speed of a journey using distance covered and the time taken. We've talked about the difference between speed and velocity, and the differences between instantaneous velocity, constant velocity, and average velocity. We've also looked at how we can deduce magnitude and the direction of velocity, both average velocity and instantaneous velocity, by looking at the slope of a line on a position time graph. That's it for this segment of Physics in Motion. I've enjoyed myself. I hope you have too, and we'll see you next time.
Alrighty. So, the parts I told you that we're going to kind of smooth over are the graphing section. We won't see that for another week, so we'll see that next week after we practice some math. And the concepts that you saw about average versus instantaneous velocity. So those are the two things you really hadn't heard much about. And I want to make sure you get those ideas. We won't touch them all that often. We're going to go with the easier of the two options, as we did with displacement over distance, to try to keep it as simple as possible, just so we can get these major ideas without too much extra work. But just to detail what the difference between those two kinds of speed are, is it's actually not that difficult to understand. Average speed is the total distance traveled divided by the total time. So that would be the speed on a trip from anywhere to Orlando. This would, if you want to think about it, generally be what we were talking about when I asked you how far away is something. So if you're an hour and a half away from Atlanta, you're assuming an average speed. right? You're assuming you're going to be going in average speed that whole time, and your GPS will do the same. So if you type any location into the GPS, what the GPS does is it looks at all the possible speeds you could go, coming to a stop at a stoplight, going on a highway, going through a neighborhood, going through a residential or not a residential, commercial area. It's going to take all that into account. It's going to average it all out, and it's going to assume you're going to go an average speed of whatever. And given that distance, it's going to take you this amount of time to get there. So average speed is generally how we sum things up. If we want to take the whole trip and sum it into a really simple, just assuming everything's even, we use average. So for this class, we're going to use average speed quite often. That'll be the one we go with. We almost always calculate average speed because if you remember back to the video, average speed was just drawing a straight line and then taking a slope of that line if we're thinking graphically. However, instantaneous speed, she said you had to take the tangent line and then take the slope of it. And I didn't want that to confuse you. It's just saying you're looking at that rate. Remember that speed's a rate of change. It's how quickly position is changing given some amount of time. So if you look at that rate of a changing rate, it's going to be really difficult to talk about the average. It's not going to be accurate. So sometimes you want the instantaneous speed, and you can think about that with what your speedometer reads out at any point while driving. So if you check your speedometer, you're going to see a given speed. That's the speed you're going in that instant. And if you sped up, it would immediately go up. If you slowed down, it would immediately go down. So it's going to be responding instantaneously to your speed at that moment. So it's just the speed in the specific instant. And that's really specific, and that's useful if you want to be specific, but kind of difficult to A, conceptualize mathematically or graphically, and B, it's going to be just a little bit beyond the needs of this class. So we're going to lean toward the average speed. All right. But that's the difference. Average is the whole sum total, just kind of smooth out all the bumps and turn it into a straight line. And then instantaneous is the speed at any given instant. So the next thing we have is we have to actually look at what this looks like, and then we have to practice. So you have 3 practice problems on your notes. You have one about a jet, you have one about a biker, and then you have one about, I think it might be a train trip. I believe it's a train trip. But we're going to work on all 3 of those right now. That's the end goal for today. And right now we have 30 minutes to do it in. I'm going to go ahead and let you know it probably will not take us 30 minutes. So the first thing I'm going to do as we go through this is I'm going to show you how to set up a problem regardless of what the problem is. It doesn't even necessarily have to be one for this class or one for physics. You can use this you can apply these ideas to any problem in life, even if it's not something for school. And I'll kind of give you some information once we see what this problem solving technique looks like. And if you can follow these 5 steps, it's going to take your confidence level hopefully through the roof that you can handle any problem. You simply have to be able to read a triangle, and we'll know what that means in a second, and then plug and chug. And so if you follow these steps, it's going to kind of do all the work for you and hopefully make it a little bit easier. So what I'll do really quickly is I'm going to highlight this. I'm going to copy this into our whiteboard. So I'm going to be doing the first one. You're going to do the second one with me, and then I'm going to let you do the third. That's generally the process. I do it. I demonstrate, show you what to do, then I help guide you through it. Then I just let you do it. All righty, we're going to go to a new share. We're going to go to whiteboard, and we're going to get started. So I'm going to clear this out. Remember that was something you saw in the video, so it got reinforced. Hopefully that made sense. We'll put it in a text box, and we're going to copy that in. All right, so this is going to be our problem, but I told you we're going to have a problem solving guide. So I'm going to go ahead and type that up for you. So the guide is actually quite simple. There's only 5 steps. And if you can remember these 5 steps, 2 of them sound so similar, they're almost the same thing. Or you could do them at once, that it should hopefully help you out. So the first thing you got to do in any problem is you're going to read the problem. I'm going to put in analyze here because that's actually what reading the problem does, is it lets you do some analysis of what you're being told and all that good stuff. So we're going to read problem. Now the next step you're going to do is after you've read the problem, it's your job to figure out what you got to do, right? That's kind of the point of that problem. So the first step that I like to do is just to identify knowns. And what this is things that you know. These are things that the problem told you or things you went into the problem already knowing. And there's going to be a couple things we add eventually that you just need to kind of keep in the back of your brain that you should always know. But right now, it's just going to be things in the problem. All right, then you're going to, well, the next one's actually not that difficult. It's really similar to the last. You're going to identify unknowns. So unknowns are going to be the things that the problem is asking for. So I'm going to go ahead and call that the solution. All right, not always, but there's occasionally in upper level physics multiple unknowns. But for this class, almost always the thing you don't know is going to be the thing you're solving for. All right, that's pretty pretty often going to be like, what is the insert value you need to solve for these given variables? And it'll be pretty clear in most of the problems we do what it's asking you to solve for. So once you've read the problem, you're going to identify what you know. You generally the numbers the problem gives you. And then you're going to identify what you don't know. That's what the problem's asking you to solve. Then you're going to, and this is generally what trips people up, is if they don't know how to do this next step, they're going to get the wrong answer. You're going to determine the appropriate tools. And determining the appropriate tools, I've got it as a non-math specific. Notice nothing here says math. These are general rules, and determining the appropriate tool is different for different problems. But for our purposes in this class, that's pick an equation. Pick an equation to plug your numbers into. All right, that's not the case for all problems, but for this one, that's definitely going to be our case. And then we're going to, what's the last step? Maybe you predicted it. You're going to solve your problem. You're going to plug everything that you've already identified in to solve for what you don't know. That's the goal. All righty. So let's apply it to this and let's see if you can follow these steps and follow what I'm going to do. So you have to set yourself up for success with stuff like this. You have to provide yourself groundwork, especially when you're getting started on new stuff, or else you're going to accidentally make mistakes. Those mistakes are going to make you feel icky. That feeling is going to make you not want to do the thing anymore, and you're never going to practice, never building those skills. So our goal is to keep you from ever feeling like that and make the groundwork as clear and concise as possible. So, so follow those 5 steps I just colored on, and we should be able to handle any problem in this class. So I want to remind you of the things that we learned throughout that PowerPoint. One of them was considering speed, like how do these things relate? That speed is equal to, well, what was the equation it gave us? Well, it said distance. I told you I'm going to write distance as an x. So when you see me write x, I mean displacement or distance, just depending on which we're calculating for. And that's going to be over time. So it's this idea of how much position change you've had over how much time has passed. That's going to be your speed. Now, I want to remind you that this is going to be written in meters per second, or really in whatever case, it's going to be the distance unit over the time unit. And that's going to be the unit for speed. So if you're not in the habit of using units, if it's something that you've never done in math or you've never done in science, it's something that you have to do in physics, because those units are sometimes just a logic check. If you end up with the wrong units, then you know you did your math wrong. So I'm going to provide you with a tool that I want you to take to your grave. Not really. I want you to keep this in your back pocket at all points, because drawing a triangle for a 3-variable equation is one of the easiest ways to conceptualize it, because it takes the guesswork out of the algebra. If you're not comfortable with algebra, and many of you are not, then this is going to do a lot of the work for you, and it just makes the process less stressful. So we're going to put this in a triangle, and the triangle tells us what to do. We just have to know how to read the triangle, all right? So this will hopefully give you a better intuition for algebra as well. So this is the original equation. When you've got a 3-variable equation like this, when you've got a rate where something's being divided by something else and it equals some quotient, you will put the thing in the numerator up top in the triangle, the thing that equals in the bottom left, and the thing in the denominator in the bottom right. And so what we're going to do to use this triangle, if you remember, we did this with density. You're going to cover up whatever you're solving for. So just put a thumb over it, just in your mind, cover it up, and you're going to look at the relationship of the other 2 variables in the triangle. So if I want to solve for speed, well, we're going to see it's going to be x over t. Well, that's our base equation, so that's good. That's definitely what we solved for. So we have one equation there that is Speed is equal to distance over time. All right, now if I want to solve for distance here, I'm going to cover it up. I'm going to look at the relationship. If you put s and t next to each other in an equation, it would indicate multiplication. So these two signify multiplication. So whatever we put down here are going to be multiplied when solving for the thing in the top of the triangle. So we're going to have this new equation that distance is equal to, and that is speed times time. I'm going to call that ST. I'm going to put the t in parentheses to help you remember that that's multiplication. And the last thing we can solve for is time, where you're going to cover it up and look at the relationship of the other two variables. And it looks like x is over s. So that means distance over speed. So if I want to solve for time, I'm going to have it as distance over the speed with which it's moving. So this is our three equations. And I'll just write this down here so we can keep them all together. I'm going to have speed equal to x over t. All right, so we have our three equations. This is your toolbox for the next week and a half. So until we add more tools, and we will add more tools, these are the three potential equations you could use to solve for some. We only know three variables right now. So this is all you got. If you can reach for these tools, if you can just make that triangle and be able to use it, or just remember these three, the triangle's a little bit easier to remember, then you can always reach into your toolbox and, given what you know, use your tool to solve for what you don't know. And that's our goal. All right, so let's do that process. So what I do is I give myself a toolkit here, and then I give myself a key. All right, my key is I've got a position, I've got a time, and I've got a speed. All right, so what are they? And then this will be where I identify my knowns. I give myself a list of variables and I start identifying them. All right, well, let's read the problem. Now we're going to do step one. What is the speed of a commercial jet which travels from New York City to Los Angeles? Well, that distance it gives us is 4,800 kilometers, and it does this trip in 6 hours. So let's go ahead and identify what we know. Well, it gives us two numbers, and you need to eventually get into the habit of just being able to recognize that, because this does not distinctly say this is distance. So you have to recognize that that meter there, this is actually kilometers. This is that prefix that means 1,000. So this is 1,000 meters. So this is 4,800 kilometers. You'd multiply by 1,000 to get meters. And we've got 6 hours. So this is definitely a time. So this is a distance. That's a time. So you identify that and you write it down. This is your key that lets you know which equation you're going to use. This is you writing down what you know. So we've got 4,800 kilometers there and 6 hours for our time. Well, let's look. We've got a change of position here, our distance, and a change in time here, 6 hours. Let's look. It's asking us to solve for. It wants to know what the speed is. So that's our question mark. That's our unknown. So that's what we're going to be solving for. Let's reach for an equation that solves for speed. Well, let's look. That doesn't work. That's solving for distance. This solves for time. Oh, well, looky there. We've got our winner. We're going to write that down. So this is us telling whoever's reading, this is the equation I'm going to use. Then we're going to plug in the values for these variables. Well, I've gotten the number 4,800 kilometers here. And then I've got 6 hours here. So notice I wrote my units in. That I wrote them there and I wrote them here. They're very important because it's going to tell me the unit for speed, because it's going to be the unit of distance over the unit of time, and that'll be our unit for speed here. So we're going to mathematically 4,800 divided by 6. Maybe you know it is 800. And then we've got kilometers on top over hours. All right. So we got kilometers per hour. So we've got 800 kilometers per hour is its speed, and this is our answer. So follow the steps. Let's go start back at the beginning. We gave ourselves a template to provide ourselves the knowledge of what we know. We read the problem. That problem gave us distance and time. We used what we knew, and then we went looking for what we don't know. We identified that we didn't know speed, and it's asking us to solve for it. So we reached for a tool, and that only has one tool that solves for speed. We used that and we solved the problem. We plugged the numbers in and then did the math. That's going to be the process you follow for all math in this class. If you can remember these 5 steps and remember your triangle, you're going to be set. All right. So just be aware that this is the case. Does anyone have questions, comments, or concerns about that? All right, so the majority of that whole problem was me showing you how to do problems. This next one's going to go faster, and the next one after that's going to go even faster. So I did this one for you. I told you we're going to do 3, and you're going to work with the second one with me. So now that you've seen it done, I'm going to ask you nicely, please do this with me. If you don't practice these skills, you're not going to get good at these skills. You have to practice them. And the more you practice, let me undo that because I want to keep those rules. Apparently, I got a little happy with the erasing. I don't mind taking that out. There we go. So please practice as I do it. So I want you writing this stuff down, even if it's just on a piece of scratch paper, even if you can't keep up in Kami, what I want you to do is on a piece of scratch paper right now, write this out. So you have until I get that question copied over to get that scratch paper. I'm going to go ahead and go back over. We're going to check our answer really quickly. All right, so well, the answer they give us is 800 kilometers per hour. That's our speed. Now it asks the second question of what would the velocity be? And remember, the velocity is speed with a direction. So it's still going to be 800 kilometers per hour as far as our number. But if you think we went from New York to LA, so we went west. So the velocity would also include the information that the direction of travel was west. So now we're going to do a question about a bike. All right, so that bike right here is our subject. So we're going to copy that question over here. We're going to try it out. We're going to follow that same process, and I want you to do this with me. This one's pretty easy, relatively. All right, you're going to need a calculator for this one. This one's not going to be, if you could do 4,800 divided by 6 and know that 48 divided by 6 is 8 and then add some zeros, you're not going to be able to do that one off the top of your head this time, or this one off the top of your head. So you will need a calculator. Unfortunately, given that I'm at home, mine's at school. So I'm going to just keep my calculator open on my phone. So when I do this, so you might want to do the same. So the first thing is you read the problem, then you're going to identify knowns, identify unknowns, and then you're going to determine the appropriate tool, which is really like use the equation that's solving for your unknown. So what is the speed of a bike that travels 355 meters in 103.7 seconds? All right, so let's identify what we know. All right, what did it give us? It gave us 2 numbers. It gave us 355 meters. And it gave us 103.7 seconds. That is a radio station here. So there we go, 103.7. Now it's asking us for speed, so that's going to be our unknown. So this is what we're solving for. So now, who would like to share what's going to be our equation? What tool are we going to use? Which equation? We're going to label this 1, 2, and 3. So of those 3, which one are we going to use?
That'd be 3.
It'd be number 3, right? So we're going to use the equation that solves for our unknown, and that's going to be speed here. So go ahead and write that equation down. So write speed is equal to x over t. Plug in those numbers and do that math. I'm going to give you about a minute to do that. So it's going to be 355. You can probably type this into a calculator faster than I can write it on this program. 103.7. Ooh, that got a little big. That's seconds. So go ahead and type that in. And what is the answer we find? What is our speed here? Who's got an answer for me?
3.42 meters per second.
There we go, 3.42. And we've got meters per second because we had meters from our distance and seconds from our time. So 3.42 meters per second. This is how you solve these kinds of problems. Notice that everything came together quite smoothly. You provide yourself this key to identify what you know, what you don't know. You identify based on what you don't know, which equation you need. You plug what you know into the equation and solve for what you don't know. That is going to be the process every time. Okay, so please make sure that you, I would suggest you write these down somewhere in that practice problem in your notes. Write these down. I mean, you can see it doesn't take much to write them down. So I'm going to erase that. And in the last, oh goodness, not the problems. In the last couple of minutes, what we're going to do is that last problem. So I'm going to do a lot less work for you this time around. All right, I'm going to read the problem and I'm going to let you do it. All right, I want you to practice this. You're not going to get good with this unless you practice. So let's go ahead and head over. First, let's check our answer. Well, let's see what they gave us. 3.42 meters per second, check. And then the velocity, because he's headed downhill, would be 3.42 meters per second downhill. Notice the shadow kind of looks like an arrow. The first time I noticed that, I thought that was quite interesting because that's how you represent velocity generally, is drawing an arrow. So even more practice. All right. So we're going to copy that in. And I want you to try this. Just go through the process, even if you did just see me show the answer. So go through your process. A train travels 100 kilometers per hour for 2 hours. What distance has it traveled? So go through your 5 steps. And again, you should be practicing this. You're not above practicing this. You're not below practicing this. So you definitely have the skills necessary and you're not overqualified. All righty. So you're going to read the problem. Identify what that problem tells you that you know. Identify what the problem's asking you to solve for. Then you're going to look for an equation that solves for that variable. You're going to plug those numbers you know into that equation, and then you are going to solve the problem. All right, when someone has an answer, let me know and let me know what you got.
At 200 kilometers.
All righty, so we got 200 kilometers. Let's look at how we might have gotten that. So let's go through that process. We're going to read where it gives us a speed here of 100 kilometers per hour. Let's go ahead and write that down. It's going to give us a time of 2 hours. So we're going to write that down here. So that 2 hours right there. It wants us to figure out what distance is. This is our unknown. This is what we're solving for. We're going to look for an equation that gives us solving for time, and that's going to be number 1 here. We're going to pull that out, write that right there. That's going to be x is equal to s times t. And then we're going to just plug those numbers in. We're going to say x is equal to, we've got 100 here. It's going to be kilometers. Now I'm going to write this slightly differently than I usually write it. All over 1 hour. So this is the exact same thing. 100 is always a 100 over 1. That's actually what that is. And then kilometers per hour, I've just put the hours down there with the 1 so that we can see what's about to happen, just to make sure we've got the right units. This is all going to be times 2 hours. Well, 2 over 1 is also how you can write 2. So we're going to say that's 2 hours over 1, just so we can have them both in fraction form. And what ends up happening is when you multiply that out, these hours cancel. So that hour cancels with this hour, and you're left with 100 kilometers times 2. All right, so 100 times 2 is going to be 200. And the only unit we have left that hasn't been canceled is kilometers. So that's where we get this answer from. So this is how you solve for that distance. These skills that we practiced today, they may seem simple, or for some of you, they may seem a little bit involved. I'm going to tell you right now that if you can just get into the habit of practicing these, you're going to be successful in the math portion of this class as we move forward. Whenever we learn a new equation, we're generally going to put it in one of these triangles. We're going to figure out 3 equations that solve for all 3 variables, and then we're going to read the problem, identify what we know, what we don't know, use an equation to solve for what we don't know using what we know. That's going to be the method. So if you can get that down, you're going to be good to go. So just to let you know, we're about to get out. I'm going to let you guys go, but first I want to tell you what you're doing tomorrow. So tomorrow we're going to have a slightly abbreviated class. I'm going to introduce this idea again, just give you one example. I'm going to run you through this process. We'll have those steps. I'll just give you the numbers. I won't give you a problem. So I'm just going to throw out some numbers with some units. We're going to look at the triangle, remind you how to use the triangle, and then I'm going to show you how to do one more problem. And then we're going to have a worksheet tomorrow that has 8 problems that are this right here. It's just solving for one of these 3 variables using those equations. And you're going to work on that in class. And that's pretty much going to be your class tomorrow. All right, so just be aware that we're going to be working on that tomorrow on Friday. So do we have any questions before we move on? Before I let you guys out? Again, I'd write those rules down if you haven't, but just wanted to open up the floor for any questions if we did have some. All righty. So we will meet 3rd period, I guess technically the 2nd class tomorrow morning, and we will go over the same concept one more time, just a quick reminder, and then you're going to start working on some problems. So we're going to put this to the test immediately. All righty, well, I'm going to go ahead